Brock's going to be moderating today.
Here I am. I'm over here. Can you see me?
Well, we see your photo.
Oh.
And then we have Helen.
Hello.
How are you, Helen?
Great, thank you.
So Helen is really knowledgeable about NGSS and helps us a lot with our NGSS content, and she's our kind of in-house expert. And then, of course, hello, Mike.
Hello, everybody. Thanks for joining us.
So, Mike, why don't we have you? I'm going to have you share your screen. I'm just going to.
Okay. Before we do that, I just want to say I cannot see the chat. Like, I've got the chat window open, but it's not showing me anyone's messages. So, as the comments and stuff are coming in, just feel free to, blurt right in, and we'll tackle it. And then there'll be plenty of time at the end for questions as well.
Perfect. I will repost them so you can see them. It's kind of a WebEx thing. And then I'll also, if I need to butt in, I'll butt in.
Okay.
I will definitely butt in, Mike.
All right. I expect as much. Everybody able to see my screen then?
It looks great.
Bright blue.
Okay. So I put a bunch of different colors in here for creative energy. That just to say it out loud, because of our banter, there should be like a Sirius XM show called Radio Rubicon, and we all have like shows during the week, and like this is exactly, we could just sit and talk about curriculum this way. It would be fun.
It would be fun.
Curriculum nerds out there. So welcome everybody. Thanks to Rubicon again for having me, and Brock and Amber and Helen for hosting. I'm sharing something today that has really just been an idea that I share with teachers and workshops, and have shared with some students, and am gearing up for some NGS workshops here in New York State, as we've got schools that are starting to align to the new standards. And I want to start by saying Happy Teacher Appreciation Week to all the teachers out there. What you do is so important, and I know that for the teachers that my kids have, they're the most wonderful people on the planet. We're so blessed by all the stuff that they do and the impacts that they have. So thank you very much to all the teachers that are out there. I also want to give a shout out to TJ McKenna. I saw that he was in on the list. I had previously watched his webinar on NGSS, and he's got a website that we're going to be sharing as part of the resources along with this one on phenomenon. And he was kind of a root of me like just noticing on my phone that I also was collecting all this phenomenon, and put some on my own website that I'll share later. So thanks for that, TJ, and I hope that I do you justice with what I'm sharing today. So let's get started. I'm going to tell you straight up, I am an absolute science nerd. I've been like this since I was a kid. And I've always had, I remember being like 8 or 10 years old, and I would have 6 or 8 aquariums running at one time in my bedroom. I was trying out like fish breeding, and trying different things and raising fish. I collected seashells. And even now, I've got close to a couple thousand seashells that are, right now they're in my shed, but I've had them at several museums and an aquarium here in Niagara Falls. On display, and I'm so interested in the way the world works and noticing that phenomenon around me, and I take a lot of pictures. This interest has been there, even my undergraduate degree is in biology, and it would have been in marine biology, but me and physics didn't get along real well. But I just had this vision of when I was a kid that I was going to grow up and be Jacques Cousteau, and it didn't happen, but I got close enough. I travel around, and I still work with science teachers, so that's all good. At this point, I've got close to 300 pictures in a folder that I've labeled Phenomena on my phone, including this picture that you see here. I'm going to zoom in on it just a little. This is a snowy owl. For those of you that watch Harry Potter, this is like Harry's owl. Hedwig. Yep. And this was taken in Lewiston, New York just a couple of weeks ago, before all the rain started and we had to start thinking about building an ark. This owl is not normally here. And so a friend posted on Facebook that this owl had been seen in the area where they live. And so I put the kids in the car and we all drove up to Lewiston, and sure enough, that owl was sitting on top of a phone pole. And when I notice things like this, first of all, I'm interested in it. And if I'm interested, then I'm engaged. If I'm engaged, I'm paying attention. If I'm paying attention, then I'm learning something. And the learning here comes from the questions that I'm asking myself and that I potentially ask children if I was using this as a teaching tool. Things like, why is this owl an uncommon sight here? Maybe something about the threshold of their range and how far south do they normally come. Has this happened before? Does it matter that we didn't have any snow in February, but in March, when it was supposed to be warming up, we had all this snow in the area, and here all of a sudden we've got a snowy owl. So when I start thinking about like the collecting of phenomenon and thinking about like what this is going to do to help students learn about the way that the world works through physical, geological, chemical, biological, all the different sciences, I think part of it is just rooted in observation and discovery versus reading about the same information in a book. I think that for science, you got to do it in order to be a beneficiary of the knowledge. You're not going to own it. It's not going to transfer. You're not going to keep it if you're reading something to learn just for the sake of a science test on Friday. Some other phenomena that I've captured are things like a red-winged blackbird here. The thing in the middle is called an American paddlefish. I took this at the Toronto Zoo, and that sucker's big, and he actually lives in Lake Erie. And probably would not want to be swimming with that, but I don't think it has any teeth, actually, because it eats zooplankton. The other thing here is a neurite. It's a mollusk. This was taken in Curacao in the Caribbean. Some other things that are on my phone are a snake skin that a teacher brought in to work with her students on. She brought in some snakes, and this was one of the snake skins that she shared. A picture of Niagara Falls frozen. And then one of my favorite pictures on my phone is this view of Highway 19 in the middle of West Virginia, and it represents these stratigraphic layers and how these layers formed over time. Then they cut them out to build the road here. And some of the layers here have coal in them. West Virginia is known for coal mining, and I'm fascinated by the way that this works. And there are some places where they're tilted up, and you can see evidence of plate tectonics and things pushing together and ripping apart. And there's places where there's like ribbons of rocks, and you can tell that because of the shape of the rocks that there's metamorphosis going on, and the rocks have been forever changed. And I'm fascinated by this view whenever we drive through West Virginia, and it lasts for like 20, 25 miles.
And Mike, if there was any question about you being a science nerd, I think you've cleared that up.
Well, and speaking of this picture in particular, there have been many times where I've stopped to collect rocks off the side of the road. And I've stopped doing that lately because when I traded my last car in, underneath the passenger side were probably a good 15 pounds of rocks where I just pulled over on the side of the road and picked stuff up. And the kids thought it was great. My wife, not so much. So when I start thinking about like phenomenon and observation and discovery level things and really wanting students to experience that level of observation and discovery, it has immediate like impact on what the NGSS is asking us to do, particularly in these engineering practices. I'm not going to read them all here, but these sort of across the board skills are things that are umbrellas for all the science that is going to be done in grades K through 12, and setting students up for college readiness if they take sciences in college. We want them asking questions. We want them developing models. We want them planning their own investigations and carrying them out. It doesn't have to be the old rote scientific method where we have a hypothesis and we test it and we gather data and we draw a conclusion and then we write a paper that is meaningless because we did something that was a canned activity. So, and this is really moving us away from that between the cross-cutting concepts, the content, the engineering practices here, what is called an NGSS 3D learning. These are things that I think that can be applied to current science practice. These, for me, represent a very contemporary angle on looking at the way that science is done, and I'm doing air quotes, in classrooms. And I want to see more of this. I don't want to wait for 6 or 7 years for there to be new science assessments. I want to see the contemporary practices now, even if you're using these contemporary practices with your current content. And I'm really honing in on a couple of different areas specifically with this webinar and what I'm proposing for using captured phenomenon on the devices that you and your students have. And those two things are developing and using models and asking questions. But everything else that's here is sort of in the periphery of the way we do science now. So even though I'm honing in on a couple, I'm still saying that all of these are really important. So let's look at the modeling first. There are several different versions of models, and these aren't all the different kinds, but these are some of the ones that you would likely see in classrooms now. Structural model, something like DNA or like a replica of something. Since yesterday was Star Wars Day, maybe an X-Wing fighter, perhaps. I'm kidding.
May the fourth be with you. That's right.
And today's Revenge of the Fifth. So,
I didn't know that. Nice.
The depth of the learning here is just unparalleled.
That's right.
Anytime you can work Star Wars into the curriculum, it's always a good idea.
So you can work it into the science curriculum. You're speaking to the right audience too.
Well, except there's all this sound in space that's not really there. So, and just for those of you who go to the movies with other people, perhaps don't mention that because I have been pinched and told to be quiet. Scientific inconsistencies in movies, and so, but I'll just leave that there. The mathematical models, especially in the younger grade levels, kids need some sort of way to visualize the conceptual learning using 10 frames or using is it Cubifix? The 10 things that I can't think of the name of them because I'm thinking of Tubifex worms because the word is similar to that, and I know it's not that. But kids need to be able to model the concepts in science so that they really own them before they start doing algebraic things and thinking divergently and more sophisticated about math. Simulations and games allow for testing of ideas and trying things out in a sandbox mode under different types of conditions to see what's going to happen. And then diagrams and drawings, which I think are probably the easiest to construct and kind of what I'm sharing today, because I've had the examples that I'm sharing today are all drawings following some sort of experience, observation, and discovery. And it's easy to do. It's easy to get complicated and sophisticated with, and it's easy to help kids to think about things beyond whatever it was they observed or discovered. And I'm going to show you an example of that in just a few minutes. Like I said before, using these models, I think, is a contemporary practice. And even if you're in a state that hasn't adopted the NGSS, how has your science instruction improved over time? And how can we make it better tomorrow? Those are some of the things that I think about when I think about doing some of these things in the classroom. Because we're looking for opportunities for our students to explore and discover and analyze. There's a companion blog post that goes with this that I wrote last week, and so I've written some more about that in the blog post, and there'll be a link to that at the end of the webinar.
We'll post it in the chat.
Yeah, I'll get it right up.
Okay, all right. And then I sent some links as well, including TJ's Phenomenon website. I'm not as gifted with the GIFs, G-I-F-S, as he is, but he's got a pretty spectacular website that everybody that cares about what or is interested in what we're talking about now should definitely go see. The next big sort of angle here is about asking questions, and this particular version of asking questions, I'm sure all of us have been to multiple PDs about asking questions in the classroom, and this version is from my new book that'll be out this fall with Marie Alcock and Allison Zamuda called The Quest for Learning, and we're talking about thinking about what discovery level learning looks like, what the endpoint is, and the multiple types of ways that we can get there by creating these learning quests that don't have really tight parameters. They're really open-ended, and they allow for multiple types of questions. They allow for social media. They allow for game design and simulation and iteration of things, and learning principles that are based on the way that our contemporary students are learning. But this is just a snapshot of the types of questions that we have in the book. Essential questions, which isn't new to anybody. A lot of people already have these umbrella type questions in their curriculum. Then we have probing questions. These are questions that are designed by the teacher and the students. They come out through conversation, you know, whether it's conversation about a discovery or an exploration or a potential for research, or the student asks a question or the teacher asks the question, and follow-up conversation leads to a more probing question, so that we can look at different ways of seeing what it is we're, like whatever it is we're trying to get to. There's refining questions where the teacher is more of the coach on the side, and these are designed by the teacher a lot of times in the moment to help students revise their thinking. And then there are driving questions, which are designed by the student, and they typically evolve over time, and they may segue in and out of each of these other types of questions. But they start off really big, and they get more and more focused and more precise as time goes on. And so from these two slides about modeling and asking questions, we're going to look at 3 different examples of phenomena that I took off of my phone and used in workshops with teachers. Or this first one is going to be with my own children in preparation for this workshop. If you've been following this on Twitter, I shared a picture earlier in the week of my own children helping me put this together, and I dropped it into the presentation here so you can see them working. But I was trying to explain to my daughter phases of the moon. And the big sort of essential question here is, why am I seeing this view of the moon? So, and you know, we look up in the sky, we see this, and just truth be told, I took this one with my Canon camera through the telescope, but I did send it to my cell phone via Dropbox so it could live in my phenomenon folder.
Sneaky.
So, and then what I'm going to share with you next is examples of models that I created with my 10-year-old, and she helped. I was doing some explaining, and they get increasingly more sophisticated as we do a model, talk about its like pros and cons, its limitations, and if we need to come to, you know, a different understanding, or if we've got the right model. Because I didn't have the right model at the beginning, and it made a difference in the way that the flow of information was happening so that it would transfer and so that she would understand. The 4-year-old also helped, but as of this moment, understands none of what I asked her to learn. And then for those of you that are out there, I don't know your grade levels, but my 10-year-old's a 4th grader, and this worked pretty well with her, but I could see this working on multiple grade levels. And then, you know, of course, the older students will be able to be more sophisticated, probably faster. So let's look at the first model. So I was trying to explain to her why we have moon phases and why we see different views of the moon. So we used images from Wikipedia and constructed this model, and actually I did this in PowerPoint. I know that's old school and very 1997, but we really were just playing around on the computer. And so I went through each of the phases, and we talked about, like, you know, she would recognize full moon. She would recognize that the moon wasn't there when it was new moon. First quarter and third quarter were easy. Well, just the quarter part, not whether it was first or third. Crescent moons, gibbous moons, she didn't really know that word, but she started using it while we were talking about this. But this viewpoint, like putting the moons around the Earth like this, wasn't really giving her the information that I wanted her to have about why the moon looks the way it does in the sky at different times during the month. So we tried something else. We switched to an app called Paper 53 on the iPad, and between the two of us, with stylus pens, we drew this out. And part of it, it started to introduce new questions about when the moon rises and when the moon sets. And at this point, we only drew the one moon here, and it was, to her, obvious that it was a quarter moon and that it started rising sometime midday and set, around midnight, so that we would see that view of the moon. But the transfer still wasn't there. This still wasn't the exact right model, and so we tried something else. And this one we did just on paper. So I got poster paper out, I got markers out. I started explaining the model that we were going to create, and you can see the little pictures of the moon there. The kids cut those out. That was actually the moon picture that I took, and we used those and glued those down to the paper. The kids colored in all the parts that they could color, and then I drew lines. And then I drew a representation of what the moon would look like from the Earth at different positions. I also discovered this really cool geometric pattern drawing all these lines, and I wonder what that would look like each day of the moon cycle. And I might do that some other time because I was interested in it. But for this one, now she's starting to see. We moved our focal point from behind the moon to in front of the moon, between the moon and the Earth, so that we could see not only the approximate times whenever the moon would rise and set, but why we're seeing the view that we see in the sky, because we've defined that with the angles here. And this is when she started to get it. This is when she started to be able to not only describe what was going on, but be able to explain why we're seeing what we're seeing. And that's what I was looking for. That's the zone that I was wanting her to be in. I'm going to zoom in just a little bit on this image here.
Mike, did you say what grade your daughter's in?
She's in the 4th grade.
4th grade. Okay. We did hear from one person in the chat. We got to give them credit, right? You have somebody in the audience that teaches grade 7. So if there's any applicable grade 7 related themes here that you want to throw in, go for it.
Well, I don't have the standards in front of me right now, but I do have the practices, and I believe I gave the link to this, to the set of engineering practices for people to see whenever we're done. So one of the 6 through 8 practices that are delineated from just developing and using models in the science and engineering practices, one of the things that the students have to be able to do is evaluate the limitations of a model for a proposed object or tool. So in this case, now I didn't know about that going in. I just know that we made a model that wasn't really teaching what I wanted it to teach. So we made another model. That model wasn't really getting there either. I could articulate it. My 4th grader couldn't articulate it because she was still in a learning mode. So, but when we got to this one, she started to be able to articulate it. Now, for a 6 through 8 student, I think that they should be able to articulate this information about why a model works and why it doesn't work, have some reflection about it, and what should we do to improve the model. And then beyond that, just in case there's teachers of higher level students, like high school students, one of the things that they have to be able to do within this practice is evaluate the merits and limitations of 2 different models of the same proposed object, tool, process, mechanism, or system, and then design another model to test the reliability of the models that came previously. And so it can be sophisticated fairly quickly. We didn't get to a very huge sophisticated place where we were being reflective about the model insofar as we stopped here, because she was getting the understanding that the model worked for her well enough to be able to understand why we see different views of the moon in the month. But since the 7th grade teacher asked, let's go back to the image of the moon that I shared previously. I'm just going to click through these. I was kind of hoping this would come up, and I planned for it ahead of time, good Boy Scout and all. This picture was taken on February the 5th, 2017, in where we live in Western New York, about 8:30 p.m. There are some further questions here and some further modeling that needs to occur. If you were looking up in the sky at night on February the 5th, 2017, approximately 8:30 p.m., you would not see this view of the moon. Your view of the moon would have been opposite to this image. I'm going to let that hang there for just a moment. And then how could you figure out whether or not I was telling you the truth? So that opens up cans of worms about how I retrieve the image. And I told you already that I used a telescope, I used a camera, and I used a series of lenses so that I could get a pretty good image. Those lenses included the lens that came with the camera, but there was another lens called a Barlow lens that actually brings in a little more light and helps me make this image that is pretty well focused. It would also be important for you to know what kind of telescope I used. I used a 10-inch Dobsonian telescope. It has a large 10-inch reflective mirror at the bottom of it, and then a system of flat mirrors at different angles to get the light to my eyes. So there's a whole other set of questions that could be developed from this, and where students could create models, including how the light from the moon gets through my telescope and to my eye and ends up being a reversed image. That'll mean that we have to begin to think about descriptions and explanations of optics and what happens when you have a concave mirror and convex lenses. Tonight when you go home, get a spoon out of your drawer, if you don't know about this, and look at yourself in both sides. One side, you're a little bigger, and the other side, you're upside down. And using that knowledge would help to sophisticate and deepen the understanding of what's going on when we're looking at the moon through devices like a telescope, and then collecting that data to interpret why we have moon phases and why the moon looks the way that it does over the course of the month.
It's fascinating. I love the idea of having students take a spoon, or predict what will it look like, and do it with your parents, because I would get it wrong, 100%.
Well, but there's more learning there. I mean, if you're just looking at a spoon, we're familiar with the spoon, and just taking a look at it. The kids do this already, but they're not thinking about the science. They're just thinking about how funny it is that they're upside down or they're a little bit bigger. But that understanding and that knowledge can be useful to transfer to understand how the light of the moon is reaching your eye in a telescope and why the image would be reversed. Because technically that image would look like a third quarter moon had I just been able to have a powerful enough camera to take it directly without using a telescope. All right, anything else coming up in the chat before I move on to the next thing?
You're blowing people's minds.
I know, I think we're all going
room.
blink, blink.
You're blowing our minds. We love it. This is super engaging, and when I'm engaged, I'm paying attention, and when I'm paying attention, Mike, I'm learning.
Excellent. That's the big takeaway. So somebody tweet that out.
Sure.
And this wasn't even the good example. So the next one I think is pretty cool. This one is an activity that deals with Newton's first law about an object remaining at rest unless it's acted upon by another force, in this case gravity. And I bought this from SteveSpanglerScience.com because I was doing some initial meetings with teachers about the ways that they can model with their students, and you're going to see some of their work here in just a moment. But we actually talked about what was happening. They tried this out. They got it to work. They were able to describe and explain it, but they were having trouble proving it. So, we just, our phones are equipped now with slow motion cameras. So we filmed it in slow motion so that we could see this ring flex, because if you pull it from the outside, if you hit it from the outside, it actually flexes up, and the hex nuts that are on top of this thing go flying. If you pull it from the inside really quick, the ring flexes down, and for a split, nanosecond, there is no force acting upon those hex nuts. They're at rest. They're going to remain at rest until acted upon by an outside force. The outside force is gravity. When gravity takes over, they drop straight down because there's nothing moving them anywhere else. And so I'm going to come out of the webinar here for just a second and share my screen with YouTube. And I'm hoping with the webinar that this works pretty well. I'm going to make this big so that we can all see it. But this is the slow motion video that we took to prove that the force that is in action here, that the ring sort of flexed inward, and then gravity took over, and you can see the hex nut drop. It's not totally crystal clear, but this is also on YouTube. It's in this presentation that you'll have access to after this is over, so you can watch it again later on your own computers. So let's press play, and it's really slow motion. It'll take a second for her finger to get up there and grab this. But here we go. So boom. When I was doing this with the teachers at one of my schools here in New York State, there was a group of students that were also in the library while we were doing this, and they were absolutely ravenous for what we were doing and wanted to be a part of it, wanted to know what in the world we were doing because they were so interested and engaged. And I told the teachers that you need to be doing this. Your kids are hungry for it, and it's going to make a huge difference in like what they retain and the conversations that they have, the models that they make, the learning that they do, and all of those are the things we want, you know, when we're teaching. So let's look at the models that these teachers drew. And again, I went from increasing, they're going to be increasingly more sophisticated. So this was one of the first drawings before anybody actually like figured out what was going on. They knew that I gave them an empty bottle, I gave them the ring, and I gave them the hex nut. I showed them how it should be set up, but I did not do the actual like movement of the ring while I was with them because I wanted them to figure it out and how they could get that hex nut into the bottle and how they would remove the ring. So this is the first one. Not a whole lot going on here. They really just described what was going on, but there's really no scientific principle here yet. It's just a description. But now I come in, you know, as the coach on the side, and I'm asking them additional questions. We may be negotiating some things so that it will lead them to a better explanation. So now we start to get a little bit of science in here, where up here in the top part where you see the rings change, where it flexes down and they've got the arrows moving, and they've got a little bit of an explanation here at the bottom that it changes from a circle to an oval, and then gravity does the rest. So we've actually got some science coming into this now, and they're all talking with each other, by the way. So they're hashing this out in conversation as well as through this drawing and modeling. And then we've got a little bit, it goes in a little bit deeper. If you look at the bottom of this, it says the force at which you hit the ring has to exceed the force of gravity, which opens up some other conversations that we can have, refinement of questions, maybe some probing questions from the students as they're doing this with their groups. And then it starts to get even more sophisticated. So, and we've got on the side here, they're writing this out. The force in which you hit the ring out must exceed the force of gravity acting on the hex nuts. The hex nuts are going to stay suspended until gravity acts on them, pulling them into the bottle. And that, you know, takes a nanosecond or so, but then it works. And so we've got, you know, we've got some good description here. We've got a good drawing, and we're starting to get into good explanation. And this is the final one here. And I love the title. Like, they know this so well, they can be funny about it. 3 nuts, a ring, and a bottle walk into a bar. And it was funny because they knew what they were doing and they knew how to explain this really well. So they drew everything out like the other groups did. They wrote quite a bit of description about what's happening, and then they wrote the explanation at the bottom. By applying the force to the inside of the ring is slightly distorted vertically. When it becomes the oval and the ring is removed from below the hex nuts, they're no longer held up and gravity will pull them down into the bottle because there's not another force besides gravity that's acting on them. And so this is pretty complete. We've got, you know, really good science explanations going on here. They're using the language of the discipline here. So this is opening up like tons of cans of worms about like literacy in the content area and how we get students to use the language of the discipline. It's like this. It's not writing up a lab report the way we used to do in 1985. This is what contemporary literacy looks like, writing out these descriptions and explanations. And
how long does this take, Mike?
I did all of this over the course of about 35 minutes.
And Mike, I have a question.
Sure.
As a teacher, depending obviously on the grade and the level of complexity, you want your students to be able to explain this model. If you introduce this topic of gravity and force with this phenomena of the hex nut falling into the bottle, and you want them to eventually get to that sophisticated explanation, would you also introduce other smaller phenomena related to this?
Absolutely. But I would want there to be some sort of like launching event. I don't want it to be that, Monday we're starting a new unit, everybody bring, fresh paper and pens. I want everybody to bring their phones and just be ready for the next learning moment. And, let's get ready to look at, maybe I do this demonstration and maybe I challenge them to go and find something similar. What can you collect on your cell phone or using whatever device you have with the younger kids, and they have like iPads in the classroom? Where can you see this in action? Where can you see this Newton's first law in action? Where can you see gravity taking over and being the force that acts upon something that was at rest? And challenge them to find that phenomenon and then bring that back to the classroom for analysis.
Okay.
So I think that it's different from, we're going to read the chapter about force in the book, and then we're going to answer the comprehension questions at the end, and then on Friday we're going to take a test about it, and you've done none of the science. You've just read about it.
Right.
I want to see lots and lots of doing. So we've got about 6 or 7 more minutes, and I want to share one more example before we get to the questions. This was from a workshop that I went to where I was the participant, and it was done by Helen Quinn, who's a professor of particle physics and astrophysics at Stanford University, probably one of the smartest people I've had the pleasure to be around. And she led the effort that produced the Next-Gen Science Standards. It was also put on with Oki Lee, who is a professor at New York University. She's a researcher around science education, language and culture, and teacher education. And Tricia Shelton, who is a high school teacher and moderates the NGSS chat on Twitter, if any of you have ever participated in that before. So what they had us do was they gave us this light box that had a place for us to look in it. It had a hole with a screw so we could pull this flap up, and it had an insert to go in. And our question was, what happens when light travels? And we used these shoe boxes as light boxes. And I think Janet and I had a conversation about this because she experienced something similar to this in a workshop that she went to, and we were comparing notes about it. It was very similar. And then here is some actual student work that they shared with us for students that they did this with. So based on looking into this light box and how much light we let into the side, we're trying to discover what happens so that our eyes can see objects. So in this case, we've got a light source, we've got the object, and because the light is reflecting off the object, we're able to see it, our brains interpret the image. Now there's some missing pieces here. So like I did before, this is the least sophisticated of the student examples that I have. When we start looking at more sophistication, this one is giving us a little bit more information about how the light waves are traveling and reflecting off of an object, but we don't really have arrows or anything here to tell us what's reflected and how our eyes are seeing it or what the connection is between the brain and the eyes. But as we go forward and students get more sophisticated with the learning, and in this case, I think the kids did the light boxes on one day, and then they had discussions about it, they did some research about it, and they came back and revised their models the way that you would revise a piece of writing in like ELA. And I think that's bloody brilliant here. To be able to create a model, knowing that we're going to revise it as new learning is happening, I think is essential. And I really like the idea of, when we do a model, it's a first draft condition, and we go back to it as we sophisticate the learning. I zoomed in on the eye part here so that you could see the connection between the eye and the brain, and look at the language that's being used here: occipital lobe, electrical impulses, iris, lens, pupil, rods, cones, retina. Now, it doesn't explain all the things that the rods and cones and retina are doing or what the optical nerve is doing, but if you look, it does show that when the light goes through the lens, it's flipping the image. So if the kid knew enough to draw that, then they likely know enough to explain it. And I think that this is like really getting into like really high-level learning. Like I said before, versus learning about this same information from a book. And then here's one that is even more sophisticated, lots of written out explanations and descriptions here, and I did zoom in on part of this so that you could see how this kid drew the model of the eye. They didn't draw the object in the back on the retina, but they wrote that light passes through the pupil into the lens. The lens focuses the light on the retina receives the light and gives the information to the optic nerve. The optic nerve sends the information to the brain where it is received and interpreted. And all of this comes about from conversation, research, refining, probing, and driving questions, and then revision of the model over time. And the descriptions are well thought out, the explanations are well thought out. This is the kind of contemporary science instruction I want to see in classrooms. So before I move into just my final thoughts here, are there any other questions, like immediate, or can people hold off for a couple minutes and we'll have some at the end?
Yeah, I think people are being pretty patient. You know, watching this, I have to say, it's interesting looking at the different examples you're showing, and I can see how it would be such a great activity for students to compare their drawings, and then they can kind of see the differences and see where, you know, how different students' understandings are showing more complexity and how that's kind of helping them reinforce concepts in their own mind. It's really cool.
Well, and it really underscores 21st century skills that don't really have anything to do with the computer so much as they have to do with communication, collaboration, critical thinking, and creative problem solving.
Absolutely.
And so they're engaging those skills whenever they work this way with these engineering practices, which is why I think that there was a really good book, one of the little ARIA books from ASCD, and I'm blanking on the name now, but it's about engineering practices in STEM. And the author's viewpoint here was that the engineering is the sun, and everything else is around it. So it's not, the focus is not necessarily on the science or the technology or the art or the math. It's on the engineering practice. And all of the other things matter, but the engineering practice and what we're getting kids to do within these engineering practices matters the most. So that said, I want to jump out of the presentation for just a second. So I want to show you what I set up, not as involved as TJ's page, but I mean, this was just sitting on my cell phone, and this is just me thinking about like the science that's around me. So in the blog post, I listed some of the questions that are here about what you could do if you're collecting phenomena, or if your students are collecting phenomena. Now I want to sing the song, Phenomena, but with
Phenomena.
Banana. You can't say people can't come here and like get a good time with this, you know,
right?
Science and nerd level curriculum.
Not singing, not at all.
So this is just a collection of photos and videos that are living on my phone right now, and I put these on here so that we have something to look at for the blog post and the webinar today. Janet sent me some pictures from her scuba diving last night. I'm going to add those to the page because they're spectacular. But there's some really cool stuff on here, including these ice pans that develop here on the shore of Lake Ontario. And it's a really neat phenomenon. It has to do with, you know, the temperature being really low and the water being relatively calm and the currents that are running through the water and creating these rings. They also created these ice volcanoes that you see here in this picture, where the frozen water gets pushed up against the shore, and then as it comes up into little cracks, more water comes up and it creates these volcano-looking structures, but it's from ice and water instead of, you know, the opposite, molten lava. We've got some video here of tetrahymena and a fold scope. I could do a whole other webinar on just these fold scopes. If you haven't looked at them yet, go to foldscopes.com and check that out. It's so amazing. The video for Newton's first law is down here. But this is available to you, and these links will be shared with you either right now in the chat window or whenever this is done and delivered as the archive. But I do have a couple of final thoughts, a few things to think about with what I've said. first of all, as I was working on the blog post and thinking about cell phones just in general and instruction, I wanted to mention how valuable Siri, Alexa, and other voice-prompted searches can be, especially the scaffold for kids who have trouble articulating the written word or getting things out of their brain. A lot of times they still can articulate it orally, and we want to give them that option of searching in that way. It's not the most efficient way to search on a phone, but it is a start, and it might lead to refining and probing and driving questions. The other thing is, just speaking of writing, science writing is a pretty high cognitive level. You're talking about evidence-based writing. You're talking about domain-specific vocabulary and concepts. And we want to be coaching students towards using the language of the content in the discipline when they're engaging all these facets of literacy, reading, writing, speaking, listening, whenever they model, describe, explain, and create. And the examples that I showed you today did show that evolution of literacy as we went from less sophisticated to more sophisticated. And just in terms of modeling and asking questions and just doing things in general in a more contemporary way, we're allowing teachers to become more of a coach and letting kids discover this stuff on their own and explore on their own, because that's how they're really going to learn it. Just knowing stuff is not a valuable skill unless you're going to be on Jeopardy. The valuable skill is doing things with the knowledge. That's what's valuable. And so that's what we want from students. If you don't have any of these engineering practices, if you don't have any next-gen science standards, but your kids are doing stuff in your classroom, they're doing their own explorations, their own observations, constructing their own explanations about it, that's what's valuable. And we need students to do that. We want them to iterate. We want them to revise. We want them to edit. And then because this is through Rubicon, I did want to mention something about documenting all of this in the curriculum. If you've got curriculum maps, there's a whole lot here that you can flesh out. There's new skills that can be layered into already documented curriculum. There's new assessments that are possible, and that would include differentiated demonstrations and products, like the models, the writing, explanations, using web tools to demonstrate and present some of this information, increased expectations for critical and creative thinking, new methodologies. Just there's a whole lot of opportunities here. And if you already have your curriculum documented, whether it's in a map or a unit plan or even just a lesson plan, there's a lot of things here to improve in that documented curriculum. Try stuff out and be reflective about it, see what works. And then, so that you can be in that process of continually reflecting and revising your own professional practice. So that's the end of the information. That it felt super quick. This always goes really quick because I'm really excited about it and very interested in it. But we do have a few minutes here. What questions do you have? What do you think?
It did seem to go really fast. I was engaged the whole time, Mike. That was really fun. We're monitoring the chat right now. We're probing people to kind of ask us the questions or maybe share examples of things that they've done that are similar, kind of looking for people to share some of that. And I think a few things are coming through here. Amber might.
Yeah, I just posted a question. It was, my question is, what types of information do you make available for students to further develop their models? Do they already have the knowledge or access to the internet, textbooks, and handouts while they develop their models? So kind of thinking through how you support that.
Okay, so access is the key here. We want them to have access to everything necessary so that we can direct the traffic. If we're not going to be the Pez dispensers of information, then we need to be the suppliers of resources to reach the right information, and perhaps, coach on the side, guide them to resources that would be relevant to their questions and their exploration. So we want to have the devices there with them, whether it's phone or iPads from the school or Chromebooks or laptops or whatever. We want to have print resources too. Traditional print resources are not going away just because I like to talk about all things digital and 21st century stuff. We still need that traditional print stuff as well, and that includes using the library, using what other resources are available, but this also includes using social media and using other people. So if the kids are engaged in this in school, is there anybody else in the school that has knowledge about the thing that they're exploring? Does the teacher have an Instagram or a Facebook or a Twitter account where they could ask questions of their network from the students? Or if the kids are older, they might even have their own accounts where they could survey their networks and find out additional information that might help them with refining, probing, and driving questions. We want to give them access to whatever they need so that the research is authentic and that the research is coming from multiple sources, because we want to be able to verify. It's not just enough to see this one place. We want to be able to verify it as well. So we want to have as much information as possible, and as much as you can give them, give it to them.
And is that, I mean, is there anything specific towards the models themselves, Mike, that you would point people to, or is that just kind of included?
Well, that came up from like the people that I've worked with, like with the adults, with my children, with the participants in the workshop that I went to. We generated that without any parameters. So it was very open-ended. I know that's a weird space for teachers, but if you'll notice, like in the examples that I shared, some descriptions and explanations were pretty specific and sophisticated, using the language of the discipline. Others weren't there yet. And those are the ones that I'm going to like go and coach and ask questions and think about you know, what else they might need to add, or something else that they might need to experience again or explore again to see if they're finding the heart of the scientific concept. So there's not really directions for what that model would look like. But if there needed to be some front loading about it, if the teacher was looking for something specific, I don't think it's a bad idea for them to model the modeling. Sometimes just showing kids like a picture of a cycle, what it looks like in a textbook, or showing them, you know, what the setup looks like, you know, that might be a good scaffold. It might be good for everybody. It just
we have another question, and that's, you know, how do you assure that kids who are on the lower side of understanding really finally achieve that higher end of understanding? Kind of thinking through the scaffolding and support. You know, some kids, they clicked, they got it. Other kids really struggle.
Well, and there may need to be some specific, like, teaching of the concept. The kids aren't getting it through exploration or discovery, and they're not getting it with additional questions, probing or driving, or maybe they were just disengaged and they weren't getting it because they just weren't sort of present in the moment, either physically or mentally. You want to make sure that you're providing additional resources for them to get this information, whether it's shared collaborative notes like through Google Docs, or whether it's providing additional information that you might share on your website or might be available in the classroom. It might be that you provide additional like times after school or before school, or, I mean, there's a lot of different ways that could play out. If it's, you know, a function of just lower level kids not getting it, then, you know, whatever you do now for differentiated practices, what scaffolds could you layer in there? Do you need to give them a little bit more front-loaded information? Do you need to make sure that they're directed towards the right resource? It would be things like that, and they would be specific to a situation. But it's probably going to be proximity and making sure those kids are close to you so that you can be more of a coach to them because they need it, and less of a coach to the ones that are moving and learning.
Got it. And then we have another question, and this is a very practical one. So any suggestions for phone use in a no cell phone school, or do you have a workaround?
Whoever is in charge of the technology committee and making that decision needs to understand that cell phones are the new pencil. If you've seen Heidi Hayes Jacobs' TED Talk and she did 20 minutes on, you know, the pencil and cell phones and devices, and, you know, there wasn't ever a time in like the 1950s where we're sending kids to the crayon lab, you know. It's kind of something that we just need to understand is a necessary component for instruction. And if we are not allowing those devices in the room, whether it's cell phones or whatever, we're limiting the learning. We're putting up a roadblock, and kids aren't really learning. We've got these places that we call school where learning is blocked. I feel the same way about like internet filters, but that's another webinar perhaps. But I really think they need to be visible. They need to be out there. If you have a policy against it, we need to revisit that policy. We need to talk to the people and, you know, understand the reasons for that policy. We need to think about ways to use this in the classroom. Bill Ferreter who is at PlugUsIn on Twitter, wrote a really cool blog post about cell phones in the classroom. And one of the things that he said in that blog post was, you know, if you want to manage this, it's as simple as putting the cell phone on the desk and not allowing it under the desk, you know, because that's when the kids are going to text and play games and do stuff. And just simply having it on the desk and visible is a huge piece of, like, management advice. Putting it into airplane mode so it can only access the Wi-Fi from the school that's protected. That's another thing, and, you know, that's something that teachers could look at the little airplane icon on the cell phone. Otherwise, you're doing this with school-sanctioned devices, like if you have a one-to-one initiative with iPads or something like that. It's kind of harder with Chromebooks. iPads would work really well to document this stuff. But it's also, you know, another workaround would just be to, you know, search Google for phenomena images, or look at my website, or look at TJ's website and other people that are saving these images. I don't think you have to collect them yourself. I just think it's really cool that I did, and that other people could potentially do that.
Well, and it's a reminder that, you know, the phenomena are accessible. They aren't these faraway concepts, that they're around us every day.
Right. You don't have to delete science learning because you don't have a cell phone to capture phenomena with.
Right. Wonderful. Well, again, any other questions from the audience as we're wrapping up? Mike, thank you so much. I'm still thinking about the spoon.
We have to go home and try it.
That will be our dinner time activity.
And then construct your own explanation as to why that moon image was reversed. So, well, thanks again to you guys for letting me sit here and spout the things that I'm interested in, and talk about some of the work that I'm doing now as New York schools begin to align to the next gen science standards over the next few years. And these are some of the things that I'm doing with teachers right now. And hopefully there was something in here that resonated with you that will be helpful for your practice. So thanks for joining me, and Rubicon, again, thanks for having me.
Yeah, Mike, we appreciate so much your willingness to share, your willingness to collaborate. I know people walked away with nuggets of information that they can apply, and it's just really a pleasure to have you come and do these with us all the time. You're always pushing the envelope and thinking of new things, and we feel grateful that you're willing to share with the network of schools that we're connected with as well.
Awesome. Well, thanks again, everybody.
Yeah, Mike, we'll be in touch. Thank you.
All right.
So just a reminder to everyone, if you joined us a little bit late, that you will be receiving a recording of this presentation in about 24 hours. And also, Helen is going to be writing a blog summary of it, so we'll have that, and that will also have a recording of the webinar that you can access later. And if you ever have any questions, please let us know. And if you would like a certificate of attendance, just let us know. Send us an email to pd@rubicon.com, and I'll put that in the chat area. And then, and then we have a quick question. Who was the speaker in the TED Talk mentioned about cell phones?
Heidi Hayes Jacobs. It wasn't
that was
about cell phones. It was about like the pencil and like the technology that we're using. And she's got a really dramatic moment when she breaks the pencil in the TED Talk. It's great.
I like the drama.
So I'm trying to check this link real quick from that Brock put in for, let's see, so that's from Educational Leadership. That's not the book, but
there was a few like back to back to back there. I was just trying to find some of the STEM-related SCD publications.
I'm looking on my shelf right now, and I think I'll let somebody borrow it. But it's about, I think it's called like Essentials for Engineering Practices, or Engineering. It might even just be called Engineering Essentials : like a question. But it's one of those the ARIA, the little books, and so it's easy to read. My inner fourth grader was all over it because I could read it in like an hour, and it was just a spectacular STEM book.
Noted. Fantastic. Well, once again, thank you, and thank you everybody for joining us. I'll throw that link in for the, is that the TED Talk with Heidi Hayes Jacobs? Wonderful. Thank you, Brock. And again, we hope to see a lot of you back soon. And Mike, I hope that we can work together soon as well.
Absolutely. There's other ideas percolating right now.
Have a good weekend, Mike. Go.
All right, y'all too. Take care. Happy Food Day, everybody.
Bye.
Bye-bye.
Bye.